So by end of the lecture of this section, you will be able to understand basics of Laplace transform, inverse Laplace transform, and the basics of circuit analysis using this Laplace transform. So how can we represent the circuit in terms of from time domain into S domain and from S domain into time domain. So from time domain into S domain, we use Laplace transform, and from S domain into time domain again, we are bringing back to time domain again. That is called inverse Laplace transform. So this is just one basic communication network model. So simply, when we talk about electronic systems or electrical and electronic systems, they are handling signals either in analog or digital form. So signals can be in terms of analog or digital. But however, signals are analog in natural, because whenever whatever the signals we have in the real world, they are analog signals, sinusoidal signals. For example, now I am talking, so I have the microphone. The microphone is sensing my voice as an analog signal. And similarly, maybe you measure the temperature of your room using sensor. The sensor is sensing the temperature in terms of analog signals. So we can say so many examples like this. So we are, because the real time or the real world signals are analog. So after we sense the analog signals and we are processing the analog signals, like for example, the measured signal, if it's very weak, then we need to do amplification. We need to amplify the signal value. For example, I measure the heartbeat using the sensor, or I measure the respiration, how we breathe, breathing rate. I use some kind of sensor to measure this breathing rate. So these signals are really very, very weak, because this is a very minute change in our chest, for example. So we need to measure that. These weak signals, after we sense it, we must amplify, and we need to filter unnecessary noises from the signals, and then we are processing. So if you really want to process the signal, all the digital processors are handling the signals in terms of digital. Digital means what? Zeros and ones, binary signals. So we have to convert this analog signal into digital signals, binary data, and then these microprocessors or microcontrollers, they can process this data in terms of digital. That is called digital signal processing, DSP. And then it gives the result. Then again, we convert this digital data into analog. So we use the digital to analog converter, and then we are seeing the data in whatever the form we want to see. Maybe you want to see in terms of graph, or you want to see in terms of numbers, the heartbeat level or the temperature level, or for example, now my voice data, you are listening as a voice data. So whatever I talk, there are so many processes are happening in between you and me. So the signals are processed by these systems and networks and this communication model. This is just like a simple voice communication. I'm also sharing the screen. So there are so many data which are converted and represented and handled and processed. And finally, you are getting the original data as same as my voice. So for everything, of course, we are processing the signals. Here, my point is the original natural signals are analog, but we need to analyze such signals through mathematical calculations. So if you really want to know what is happening to these signals, of course, you need to study about the in-between technologies, whatever we use in this communication network, and how they process the data. So of course, it's always the best to analyze the signals in terms of mathematical calculations. So Laplace transforms helps such analysis and calculations. So it supports the way we learn and analyze circuits. Devices are interconnected to form a circuit that we know. So many devices are interconnected. For example, if we talk about one filter circuit, so we are connecting so many different capacitors and resistors and operational amplifiers, and we are building or we are constructing one circuit. And there are some constraints like resistance, inductance, impedance, admittance. So there are several constraints on each individual devices. So where each device has a mathematical relationship between the voltage across the device and the current flowing through the device with respect to its with respect to its constraints, right? Let us say you have a capacitor and you are applying the voltage and the current is flowing through the capacitor. So the current flow is different or it can vary based on the capacitance value of the capacitor, right? So how can we do analyze this? Now we are talking in terms of theory or just like a normal sentence, but we really want to know what is happening. So for that, we need to have some kind of mathematical analysis. We need to know the mathematical relationship between the capacitance and the current flow, or the capacitance and the voltage across the capacitor. So Laplace transform or LT, it really helps us to study such circuits in the S domain. S domain is, remember, you can represent the system in time domain. So because whatever the signal input you are applying, you are getting some output. So with respect to time, so I apply the input at first, now maybe that 11:38, or I'm getting maybe after few seconds the output. It's really depending upon the system performance. We always prefer high performance systems with as less delay as possible, right? We can wait only maybe microseconds or milliseconds. We cannot wait in terms of seconds or minutes. So we want very fast response. But anyway, so we are applying the signal and we are getting the output with respect to time. So, but when we do this kind of analysis, we have to also consider the frequencies. So then the Laplace transform is the best method to analyze such circuits operation. And of course, it uses some algebraic techniques. So algebraic equations that maybe you have already studied in your mathematics course 1 and 2. And also we use some KCL and KVL. KCL and KVL, that is a Kirchhoff's current law and voltage law. Maybe you have studied in your network theory course. So we will use everything in this Laplace transform analysis. So then you can easily transform the IV constraints of the devices. So here, as I mentioned here, each device has its own constraint. Of course, we are using different devices to build the circuit, and each device has its own constraint, and each constraint has certain relationship with voltage and current. So we have to form some kind of polynomial equations, algebraic equations, in order to analyze the relationship, mathematical relationship between the device property and the current flowing through it, or the voltage across the device. So for that purpose, Laplace transform is very useful. So it's very useful when you deal with time variant linear systems. It means there is the Laplace transform. You can express what the system does to an input in terms of a transfer function. You know what is transfer function? And just before we have studied about the transfer function with respect to frequency considerations. And if you make the Laplace transform of the input, then you can get Laplace transform of the output by simply multiplying the input Laplace transform by the transfer function. So we will see that when we see this problem, then you will understand what does it mean. So it's kind of very simple way to use the Laplace transform to analyze the circuit. So simply it turns convolution and makes it possible to solve a constant coefficient linear differential equations. For example, for output for given inputs, or look at the stability of the circuit, or develop controllers. So there are so many examples actually. So let me just tell you one simple example to understand this instead of going through these sentences. Let me take my pen. So now let us take one simple example, electronic circuit or electronic system. Which one we can take now? Maybe let's take rectifier. So rectifier means what? Let us take one half wave rectifier. So what is the function or the purpose of the rectifier? Rectifier will convert AC voltage into DC, alternate current into direct current, right? Okay, so AC into DC. What is AC? AC is naturally analog signal, that is a sinusoidal signal. So I am applying the AC sinusoidal input, that is the input. At the output, I am getting direct current. X-axis, Y-axis. Okay. So technically, this is not exactly pure DC. You see here, pure DC is like this. But here, the voltage is like this, and then like this. It's called pulsating DC. And then we have to use some filters and regulators and convert this pulsating DC into this pure DC. That is a different operation. So what I wanted to tell you here. So now I have to calculate the output DC voltage. So how can I calculate that? So I need to do, I need to find the average of all these pulsating DC voltages. For example, now I apply plus 5 volt and here minus 5 volt. So minus 5 volt, I don't care because I don't get any output. This plus 5 volt I am getting here. So plus 5 volt, plus 5 volt, plus 5 volt. But remember, this is not a discrete value. This is still it's an analog signal. This is the continuous wave. This is not discrete samples. This is a continuous waves. So if I calculate from this point to this point, I have infinite number of samples. So I cannot make the easy or normal average calculation. So how can you make the average of any three numbers or any number of any numbers? So let us say like we have 5, 5, 5. How can you make the average? 5 plus 5 plus 5, that is 15. And then the number count. So addition of all the numbers divided by the number count. So this 5 plus 5 plus 5 is 15. The number count is 1, 2, 3. I have three numbers. So then the average is 5 volt, right? This is the normal mathematics. How can you find the average of different values? But here I cannot use this simple or the straightforward mathematics. So here I need to use some kind of special mathematics operator. For example, I need to use integrator. What is the function of integrator? Integrator will integrate everything. So I use integrator and then 0 to 2 pi. That is the time period of one full cycle. So this is the 0 and this is pi and this is 2 pi and this is 3 pi and this is 4 pi and this is 5 pi and so on. So one full cycle, if you talk about one full cycle, that is the period is 0 to 2 pi. So I am making 0 to 2 pi and whatever the output I get here is just this one. So this one is the Pm sine omega t dt. So sine is representing the sinusoidal waveform. Vm is representing this 5 volt. That is the magnitude of the input signal. So if I use this formula and solve this, then I can get the system response. I mean the half wave rectifier response here. That is how we have to do the mathematical analysis. Now I am doing everything in the time domain. Now I can convert this into Laplace S domain. So this is what I mentioned here. The simple convolution or simple mathematics cannot be used in this kind of circuit analysis, because now here we are analyzing the output of the circuit. So we need to use some kind of special mathematical operators together with special kind of transforms. Like you have studied maybe about Fourier analysis, Fourier transforms, Laplace transform, Z transforms, and so on, right? These all are special mathematical operators. These are special mathematical transformations that works together with integration or differentiation. Then we can find the system response. So that is how the Laplace transform. The Laplace transform is one of the method. It's a very useful and practical method to analyze the system output with respect to frequency.